We are discussing about the different types of atomic radiuses. The first type of radius is covalent radius. Consider, and whenever you say covalent, it is the bond that is made between two nonmetals. So consider two nonmetals are coming close with each other. It could be either homonuclear, also heteronuclear. What do I mean by this term? It could be hydrogen. Two hydrogens coming together to form H2. It could be H and Cl coming together to form HCl. Both are covalent here. So consider they two are coming close with each other. Okay, they are trying to come to close with each other. They are trying to understand how will a bond get formed at first. I have, let me say, I am talking about hydrogen atom. That is in another hydrogen atom. Hydrogen atom. Each hydrogen atom is having one electron each. So at first, this nucleus will be attracting this electron. Correct. This nucleus will be attracting this electron. Right. Its own nucleus will be attracting this electron. Its own nucleus will be attracting this electron. Absolutely. So we are all looking only for the attractive force here. What about repulsive force? That also should work here. Where will it work? The two electrons should repel each other because of the same charge. The two nucleus should also repel each other because of the same charge. So repulsive force is also happening there. Two forces are happening, attractive force and repulsive force. So they are trying to come close with each other, but the repulsive force is also stopping them. So at a particular distance between their nucleus, what happens? The attractive force becomes more than repulsive force. Only at exactly certain particular distance between the two nucleus, this happens. At this distance, the bond is formed. At this distance only, the bond is formed. So the distance between the two nucleus is what is called as bond length. The distance between the two nucleus is called as bond length. So if I am taking the bond length, I divide it by 2, what I get is covalent radius. I am discussing about hydrogen here. Both are non-metals. They are trying to come close with each other. Look at this page here. At certain distance between these two nucleus, this is D. People also say L. Both are same. At certain distance only, what happens? Attractive force overcomes the repulsive force. The bond is formed. So if you are going to ask me to calculate the covalent radius here, I will say it is bond length divided by 2. Because I am exactly talking about this length. Similarly, I am exactly talking about this length. So what do you understand here? In covalent radius, they are trying to manage themselves to overlap with each other. You can see this here. They have actually overlapped. This is covalent radius. Let us discuss about metallic radius. I am talking about the metal atoms. Let me say I am talking about Fe, which is managing with another Fe. At certain distance between the nucleus, they formed a bond. And this is called as bond length. You can see they didn't merge. They didn't overlap. They're coming at most close as possible. That's what is happening here. And such radius is called as metallic radius. That radius will be called as metallic radius. Understood?
Yes.
Yes, ma'am.
Yes. So the term crystal radius is used to denote the size of the atoms in the metal. People also address this as crystal radius, metallic radius. It is telling you about the size of the atoms in the metal. Metals, you know, were very closely packed spheres in the metallic crystal. We always assume these atoms are in spherical shape. So we say they are closely packed in a metallic crystal. The metal atoms are supposed to touch one another in a crystal. You can look at this. They're touching one another in the metal crystal. Metallic radius is defined as 1/2 the distance between the center of the nucleus of two atoms in the metallic crystal. Same formula only. If this is a D, then metallic radius will be D by 2. Now, how will I be able to calculate this, determine this metallic radius? You can do it by X-ray diffraction method, which is also abbreviated as XRD. What is XRD? I am having a metal lattice. What do you mean by lattice, Nitish?
Like a layer of sheets in a pattern.
Ah, yes, very good. It's a pattern of arrangement. Can I say that?
Yes, ma'am.
It's a pattern of arrangement of the metal here. I am sending X-rays on it. Very powerful radiation, isn't it? It will hit the metal and it will be ejected or reflected. Can I say that?
Yes.
So consider I am giving H nu as the energy. The ejected will be having H nu dash. With respect to H nu dash itself, I will be able to tell you what metal was there. Number one. With respect to that, I will be able to say the interlattice distance. This distance, you can see two patterns are going as Nitish says. Between them, the distance can be found. Not just that, I will also be able to calculate the metallic radius as well by XRD method. The metallic radius is about 10 to 15% higher than the single covalent bond radius of those elements. Lakshana, justify why it should be larger than covalent radius.
It should be larger so that it does not overlap each other.
No,
Like,
no, no, you are saying the consequence as a cause. They are saying metallic radius is usually 10 to 15% more than covalent. Justify why? As you said, in metallic they didn't overlap. No overlap is happening.
yes,
But in
ma'am.
covalent radius it overlapped. So it's obvious that there should be higher one. Correct?
Yes,
So in
ma'am.
other words, can we say the single bond covalent radius is smaller than the metallic radius due to no overlapping of atomic orbital in metallic bonding?
Yes, ma'am.
Yes. Mridula, did you understand her?
Yes, ma'am.
Right. So we discussed about.
Ma'am, can you go a bit up?
Hmm. Okay.
Yes.
Right. Now the third type of radius. We are discussing about the last type of radius called as van der Waals radius. Look at the difference here. In covalent, they've overlapped. In metallic, they managed to come very close with each other. In van der Waals, can you see they are distant away apart?
Yes.
So shall I say van der Waals radius will be larger than metallic radius, which will be larger than covalent radius?
Yes, ma'am.
Yes, ma'am.
So this word van der Waals radius talks about the gases, basically noble gases, which do not want to, which cannot come very close first of all, isn't it? They cannot come very close at all. So we are generally talking about the noble gases here. Let me say this is helium, this is another helium at certain distance between each other. They are trying to come as most close as possible. That is called as van der Waals radius. So let's go here. However, the atomic radius of inert gases are expressed in terms of van der Waals radii.
Ma'am.
Tell me, Pa.
Like is this van der Waals radius formed by a special type of bond, or it is like part of covalent or metallic?
Van der Waal is never a bond. It is just an interaction. It's a weak interaction.
Like a weak attraction between two atoms.
Ah, exactly. Just like saying
Okay.
hi to each other. Hello. Just like that.
Okay.
Okay? Metallic radius is inversely proportional to metallic bond strength. Metallic radius is inversely proportional to metallic bond strength. So more stronger it is. It means the metallic radius is very small. When will something be very stronger? When they are very close with each other. Only then they will be very stronger. Correct?
Yes, ma'am.
Yes, ma'am.
So make a note of it.
Ma'am.
Yes.
And what about ionic bonds, ma'am? Do they have the same similar type of radius, or they don't even
No.
have a radius?
No, they don't. You can't calculate it. For
Okay.
ionic radius, you have a special kind of a formula to calculate it. Okay.
Yes, ma'am.
For non-metals, atomic radius corresponds to covalent radius. For metals, atomic radius corresponds to metallic radius. For inert gases, atomic radius means van der Waals radius. Okay. So visualizing the van der Waals radius here. I am talking about not just inert gases, any gases you can take. But
Ma'am,
preferentially
could
it
you
is
show
in.
the previous slide?
No.
Yes, ma'am. Thank you.
1 minute, right? You can just look at this slide here. I'll be back. Hello. Yes. Amre, I'm in a class, ma. Can you please call me after 7:30? Okay, da. If you want, you no. If you want, you can just join the class. I'm doing covalent radius. If you want, you can join it. Periodic properties. Yes, I'll share you the link. Yeah, we are looking at the van der Waals radius here. It's not specific only about the noble gases. Any gaseous molecule for that matter. So look at this here. Chlorine has got covalently bonded with each other. Chlorine is a non-metal, isn't it? First of all. So the two chlorines are bonded. It's covalent radius between them. Similarly, it is a covalent radius. Now, this chlorine comes close with this chlorine. Now, if I'm looking at the bond distance between them, and this is what is called as van der Waals radius. So, van der Waals radius is twice that of covalent radius. Okay, ma? Right. So the
Yes,
name
ma'am.
van der Waals radius is used because of the force existing between the molecules are called as Van der Waals force of attraction, very weakest force of attraction. Van der Waals forces are directly proportional to molecular weight or atomic weight in with respect to inert gases. So if they are giving helium, neon, argon, krypton, and xenon, the van der Waals forces are maximum in this order. So when do you expect them should be so maximum here? When you are seeing it in a solid state, van der Waals forces are maximum. And almost in the gaseous condition, it is very absent here. Ma'am, you just now mentioned you are talking about the chlorine gas here. Then how do you say it is absent here? You cannot calculate this van der Waals forces or you cannot determine this van der Waals forces with gaseous state. You have to condense them to the solid state or at least to the liquid state so that you can study this. Okay, so van der Waals radius determination can be done by solidifying the gas. By solidify the gas, I will be able to find it out. In liquid state, the magnitude is very small. So van der Waals radius is determined in solid state only. So what am I doing? I'm solidifying the gas. How can I solidify the gas?
Cooling
Mridula,
it,
how can
ma'am.
I solidify it? Nitish, wait, let Mridula answer. How can you solidify it?
Ma'am, increase the pressure.
Very good. Then decrease the temperature.
Yes, ma'am.
Yeah. So pressure should be increased and temperature should be decreased in order to obtain this van der Waals radius here. Okay. Van der Waals radii is also known as non-bonded radii because there is no particle bonding here. It's just an interaction force that's happened between. So it is a non-bonded radii. Van der Waals radius is also determined by X-ray diffraction studies. We have mentioned already XRD. In molecules of non-metals. That means I'm talking about gaseous non-metals. Both covalent and van der Waals radius exist. Yes, we just now saw here. Covalent was also there. Van der Waals was also there.
Ma'am.
Tell me that.
And won't these X-rays like deflect those atoms and make them separate because they are like very high energy, ma'am? Those van der Waals forces are
We
like
will
very
be
weak, right?
very good. I am not doing it in the gaseous state. I'm actually solidifying them. That means the intermolecular force of attraction is increased at that time.
So we cannot find like the radius at gaseous state.
That's not possible. That's what is here said. The forces are
Okay, ma'am.
maximum in the solid state. Yes. So van der Waals radius is always greater than covalent radius and also greater than all of known radius. So I would say covalent radius will be the highest one, isn't it? Covalent
Yes, ma'am.
radius because of the overlapping is happening, followed by metallic radius, followed by the van der Waals radius. So here they are provided the experimental internuclear distance in the chlorine molecule is 1.98 Armstrong units. What will be the covalent radius here? As I told you, this is a bond length. Internuclear distance is nothing but bond length, this distance. So what is covalent radius? Isn't it half of it? So just calculating the
Yes.
half of it. There is another formula here to calculate the individual atoms that has participated. Let us calculate. The formula is Stephenson's formula. Bond length between A and B. There is an atom is here. B atom is also there. So we are calculating the bond distance between each. Radius of A plus radius of B minus 0.09 chi A minus chi B, where the chi is nothing but electronegativity of the particular element. Electronegativity of the element is given as chi here. This 0.09 holds good for Armstrong units. If at all they have given you some other radius or d value is provided, yeah, you can measure this. You can convert this into particular value. If it is in, ma'am, it is in nanometer, convert it accordingly. Let us calculate the covalent radius of hydrogen using the experimental d value, which is 1.28 Armstrong. So they are talking about HCl molecule here. Hydrogen and chlorine are coming close with each other to form this covalent bond. They are given you this d value. They have provided the d value here, which is 1.28 Armstrong, and the covalent radius of chlorine is provided. How much is that? 0.99 Armstrong. In Pauling scale of electronegativity, there are various scales here. Alfred Rochow, Pauling, Mulliken, many scales are there. You will learn it. In Pauling scale of electronegativity, the electronegativity of chlorine and hydrogen are 3 and 2.1 respectively. Has to calculate the covalent radius of hydrogen. So use the Stevenson formula. D value is provided 1.28. You are asked to calculate the radius of hydrogen. Radius of chlorine is provided 0.99. There is some mistake here. You can just substitute the value that is provided here minus 0.09 chi of Cl, which is 3 minus 2.1. From there, calculate the RH.
Ma'am,
Yes, sir.
and what is electronegativity actually means for an atom?
Yeah. We didn't touch the topic yet. Since it is here, I'm just telling you plain. When we go, we will do it broader way. See, when break the word electro and negativity. Electrons are negatively charged species. So if we are adding electron to any element, will they carry a negative charge?
Yes, ma'am.
X is there. I add electron to it. Do you say X minus? Yeah.
Yes, ma'am.
Right? So the tendency of an element to attract the electron is called as electronegativity.
Like
How
a
much?
reaction, like the tendency of an atom to like attract the electron, like in redox reaction.
Yes. We are talking about a single element here, not about a compound.
Okay, ma'am.
Okay. So there is a chemical bond. For example, I'm saying, ma'am, I'm having HCl, ma'am. Here, this is a covalent bond. Hydrogen is also a non-metal. Chlorine is also a non-metal. You know, non-metals do not like to provide electron. They always want to take the electron. But still, chlorine is very electronegative here. It likes to pull electron towards it from hydrogen. So that hydrogen becomes delta plus and this becomes delta minus. This sign tells you the electronegativity value. I say it is positive because hydrogen is losing its electron cloud towards chlorine. I say it is negative because chlorine is pulling the electron towards it. So electronegativity is basically a property of an atom's ability to attract the shared electron. It is already in a shared electrons towards itself within a chemical bond. I already formed a bond here, but still it is pulling the electron towards it. This is called electronegativity.
Okay, ma'am.
So here again they are giving for the metallic radius, same formula only. They are giving you the distance between the adjacent copper atom and solid copper is 2.56 Armstrong. What will be the metallic radius of the copper here? The bond length is provided. Just divide by 2 to get the metallic radius of copper. Okay. Now we are discussing about the atomic radius pattern or trend in a periodic table. So usually our trend is going to be ATP DTG along the period down the group. Along the period down the group. Ma'am, what are you talking about? Look at this. I'm taking the second period. lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. I am discussing about along the period here. So let us start writing the electronic configuration. What do you write? It is 3, right? 4, 5, 6, 7, 8, 9, and 10. So how do you write it? 2, comma 1. I'm not writing quantum electronic configuration, normal electronic configuration. 2, comma 1. What about it? 2, comma 2. What about this? Correct?
Yes.
Yeah. So you write as 1s2 2s1, 1s2 2s2, 1s2 2s, 1 2p1. What about this? So 2s2, 2p2,
Yes.
2s2 2p3, then this one 1s2 2s2 2p4, this 1s2 2s2 2p5, the last one 1s2 2s2 2p6. What are you doing actually? We can see the next electron that you are adding is getting added in the same shell itself. Can you see this?
Yes, ma'am.
Still they are in the second shell only, L shell. I am seeing they are all getting added in the same shell itself. Am I right?
Yes, ma'am.
Right. So here there is no addition of subsequent subshell has happened. I didn't put my electron into the third shell. Still my electrons are in the second shell itself. I have a nucleus. If it is lithium, I say there are 2 electrons here and 1 electron is present here. When I said beryllium, 2 electrons here and 2 electrons in the second shell. Again here in boron, 2 electrons here and 3 electrons in my third shell. Am I right? Totally how many are there? Valence shell. 3 electrons are there. Correct, Appa?
Yes, ma'am.
Yeah, look at for carbon, 2 electron and 4 electron in my second shell. Can you see I am adding the electrons in the same shell, first point. Also, I can see the number of electrons is continuously increasing in the same shell itself. Am I right?
Yes, ma'am.
Correct or not? Mridula, did you understand, Ra?
Yes, ma'am.
Yeah. So because of this, what happens is that there is no screening effect. There is no screening effect. Okay, what do you mean by screening effect? See, I'm having a door, I'm having a window in my home. I want to screen the sunlight. I don't want the sunlight to penetrate at me. So I put a curtain so that it screens it. Similarly, this nucleus is having highest positive charge here. There is a first shell here which is having 2 electrons. This is shielding the nuclear force of attraction. Nuclear force of attraction on the 1 electron that is present in the outermost shell. What about here again? Same 2 electron only, ma'am, which is shielding the 2 electrons here. Again here, same 2 electron only, which is shielding the 3 electron. What about here? Same 2 electron only, which is shielding this 4 electron here. Understood? So I can understand there is screening effect, but limited screening effect is there. Not much.
Ma'am,
Same screening.
what is the meaning of screening effect?
What did I tell you now? What did you understand with the explanation I gave you? There is a
That
window. I am putting a curtain. What do you understand from that?
that two electrons are shielding the
Hmm.
remaining electrons which are present in the next
Balance shell.
orbit. Yes,
Hmm.
ma'am.
So that the effect that you are seeing here is called a screening effect. It is
Okay,
like
ma'am.
it is acting like a screen here. People also call this shielding effect. Both are same.
Okay,
Screening
ma'am.
effect, shielding effect. So along the period I move, I can understand no addition of subsequent shell has happened. Also, the screening effect is constant here, isn't it? It's constant. 2 electron only is there. So therefore, what happened? The nuclear force of attraction gradually increases. Slowly it is increasing. Why, ma'am? If it is constant, don't you think the nuclear force of attraction should also be constant? But this fellow nucleus is carrying a positive charge, very greedy boy. He is carrying positive charge. He is very happy to see many electrons. Initially there was 1 electron, now 2, now 3, now 4. The nuclear force of attraction increases as the electron count increases gradually. Do you understand?
Yes, ma'am.
Yes. So we are trying to learn why along the period the atomic radius is decreasing. Okay, ma'am, we didn't end the point. We just said nuclear force of attraction. So consider I'm having this positive nucleus and this electron is there. Slowly what happened? The nuclear force of attraction is increasing. Leave out till neon. Slowly the nuclear force of attraction is what is happening? It is increasing. So this is positive, this is negative. It is just like a magnet. So this tries to pull this electron cloud very close to it. So if it is trying to hold the electron cloud very close to it, don't you think it will shrink?
Yes, ma'am.
So only the radius decreases. So can we say,
Ma'am.
tell me, Pa,
But isn't there other electrons before its orbital which can push back it again?
which electrons?
Like if an electron is there in 2s,
Hmm.
then won't the electrons in 1s push it
But minimum only. They will be
or like
according
very
to
less compared to
very
nuclear?
less, very less compared to your NFA.
Okay, ma'am.
Okay. So we are writing a point here. NFA is inversely proportional to radius. If NFA is more, radius will be small.